All right. All right, so it's the last lecture. It's Friday afternoon. It's officially afternoon. The last lecture is about halo occupation models. So this is an alternative to subhalo abundance matching. So I mentioned a couple of limitations of using subhalo abundance matching as a sort of precision tool. Yes, it's a non-parametric, or there are very, very few parameters, but you actually need some flexibility if you would want to bring to bear your model on the quality of the data that Will showed us from Desi in the previous lecture. And so sham can actually be too inflexible in order to sort of capture the complexity that we see in the data. Another major limitation of using sham is the reliance on subhalos places stringent demands on your simulation. So what you're looking at in this figure is a plot of, in dash curves, the NFW profile, just this, the NFW profile of a dark matter halo of, I think, Milky Way mass is what's shown here. And the circles or the triangles show the radial distribution of subhalos, actually simulated subhalos, in either Bolshoi or Elvis or high resolution n-body simulations. And you can see that in the interior regions of the halo, it's very small radii, you're even like an order of magnitude off of the abundance of subhalos from the NFW profile. Now, of course, who knows the NFW profile is the correct description of satellite galaxies. It does actually give a good fit to two-point clustering, which I'll show in a few slides. This is suggestive that there is either a mass resolution problem with finding subhalos in the interior regions of halos, and or just a numerical problem with the algorithms that are used to identify subhalos. And it's easy to understand why it might be very challenging, even for, so these are rockstar subhalos, even for a sort of state-of-the-art modern subhalo finder like Rockstar that uses 60 phase space information. In the interior of a halo, there's a steep gradient in the potential, and you're looking for a small bump of a subhalo about that gradient. This is just an intrinsically hard numerical problem when you only have a subhalo which has even a few hundred particles. And so it's just numerically very challenging to have sort of resolved and converged subhalo abundances and their radial distributions for purposes of subhalo abundance matching. There's lots of active research in this area, looking for sort of quantifying the extent to which this is a problem, and then also looking for sort of solutions to traditional subhalo finding. I've given links to several of these here. I would mostly like to move on to talk about a sort of long-standing alternative solution to that problem, which is just to simply ignore subhalos entirely and use only host halos in your model of the galaxy halo connection. And sort of a general term for this approach to the galaxy halo connection is called halo occupation modeling. It just refers to the fact that you're taking a halo here, I mean host halo, and you're just sprinkling in galaxies such that they occupy that host halo according to some scaling relation. So the most widely used model of halo occupation models for purposes of cosmological inference is the HOD, so it stands for halo occupation distribution. And basically, if you have seen a galaxy halo connection model, a nonlinear regime that derives cosmological constraints, there are a couple of exceptions that I'll show towards the end of the slides, but it's overwhelmingly likely that what you're looking at was an HOD model. It's the most widely used model in that context because it's so fast, and also because it asks the least of the underlying simulations. You really just need to resolve host halos in order to implement an HOD. So, okay, we had this nice method in subhalo abundance matching for the way in which we derived the stellar to halo mass relation just by rank ordering galaxies by mass and halos by mass, and then reading off the number densities to provide the correspondence. So where do we get functional forms for the HOD? So the HOD describes just number of galaxies in a halo. So what galaxies? Well, it depends entirely on your sample. If you have red galaxies or blue galaxies or high mass or low mass, then you have a different scaling relation for how many of them should live in a halo as a function of mass. So where do we get these scaling relations from? Historically, we used subhalos in order to motivate the functional forms for the HOD. So this is from one of my all-time favorite papers in the galaxy halo connection by Andrei Kravtsov, the dark side of the halo occupation distribution. This is a transformative paper that contains many landmark insights that I think were then built upon for many years to come. One of the many things that this paper did was it said, let's take a catalog of a subhalo catalog, which is at that time in 2004 was quite a new technology. And let's make a cut in Vmax and say above that cut, let me just count the number of subhalos that live in host halos as a function of the host halo mass. So at that time, even though the famous Booyah result from Charlie Conroy was still 2 years in the future, at that time it was, so Andre was on that paper with Charlie Conroy in 2006, it was known that Vmax was probably a good proxy for galaxy mass. And so they used a cut in Vmax to essentially mock up a threshold for galaxy mass and number density. And then they just counted the number of subhalos as a function of host halo mass. So that's what you're looking at in this figure. Host halo mass in the horizontal, number of subhalos in the vertical. Separately shown for central subhalos, in other words, whether the Vmax value of the host halo in question exceeded the threshold, and then for subhalos. And what they saw was this characteristic shape of essentially an error function for the number of central galaxies. So it smoothly rolls from at large mass halos to unity, and then smoothly rolls to 0. And then a power law shape with a cutoff at low mass for satellites. So these are the sort of classic vanilla HOD 5-parameter type model for the way in which NSEN and NSAT scale with halo mass. So this functional form was developed sort of independently amongst several different authors around the same time. Andre and company did this for using subhalo occupations to sort of motivate the functional form. Zheng did this in sort of parallel work using sort of early models of smooth particle hydrodynamics, a hydrodynamical simulation at the time, to then count as a function of a threshold in galaxy mass, how many galaxies as a function of halo mass live in a dark matter halo, and found the same basic result of an error function type scaling relation and a power law for satellites. And we repeated this also not just for SPH hydro simulations, but also a semi-analytic model at the time, again seeing the same characteristic scaling relation. So certainly the error function is quite intuitive for where it should come from if you just think that there is some scaling relation between stellar mass and halo mass and some log normal PDF that gives you some scatter about that scaling relation. Well, so NSEN as a function of halo mass is just an integral of that. And an integral of a Gaussian is an error function. And so it's sort of intuitive that once you go to sufficiently high mass, you have enough halos, or you have enough mass in your halo such that you're going to have a galaxy that sits at the center of that halo. And so it's natural that it asymptotes to unity, and also natural that it asymptotes to 0, such that once your halo is sufficiently low mass, there's no way that you could have a galaxy of a given mass that fits in that halo. And so I think the basic scaling relations are intuitive and are sort of supported from subhalo abundance, from hydro-simulated galaxy mass, and from semi-analytic model simulated galaxy mass. So these are our motivating functional forms. And again, the idea is we use sort of physics-based motivation for what form our function should have to control these scaling relations. And then we go to observational data to tell us what the best fitting parameters should be. This is a very common theme throughout these lectures. This is a sort of famous result from Edith Zahavi, really, I think, demonstrating the power of the HOD to describe a wide variety of galaxy samples. So this is she was using the HOD to describe galaxy clustering in the Sloan Digital Sky Survey as a function of different luminosity thresholds, which is what's color-coded in this figure. And she used the same exact functional form again and again and again and re-optimized the parameters for very faint samples, very bright samples, and everywhere in between. And then you're just looking at how the basic scaling relations of the underlying HOD change as you change the threshold of the sample. So the general takeaways here are, let's look one more time at these functional forms. You have some minimum halo mass below which you have essentially have no central galaxies, and then quickly as you exceed that mass, you have one central galaxy. There can only be one central per host halo, and then some scatter about how quickly you make that transition, and then essentially a power law with a power law index. So, oops, wrong way. So the basic result of the scaling relations when fitting to observational data is just that if you're fitting to brighter and brighter galaxy samples, you need a larger and larger halo mass in order to have a central. And then generally, as you have larger and larger mass halos, you have more and more satellites that fit in that halo. So let's see. Sort of rinse and repeat, but now rather than for luminosity-dependent clustering, for color-dependent clustering. So you can similarly repeat this exercise and just fit your HOD functional forms to color-selected galaxy samples. And this is what was also done in the same paper. So Edith did this for different gradations of, I'm pretty sure it was G-R color, from reddest to next reddest to next reddest, all the way down to bluest for a particular threshold, a particular bin luminosity. And again, found good fits to the 2-point clustering using the same sort of vanilla five-dimensional model. Finding one basic takeaway is just that in higher mass halos, you have redder satellites. And in general, you have, as halo mass increases, you have redder galaxies. Great. Okay, so this is the HOD. And maybe one feature I want to remind you of is that in the HOD, the galaxies have no attributes. So imagine what you would do in order to, in a simulation-based implementation of the HOD, in order to make a universe with the HOD, you would take a host halo catalog. You would pick your parameters according to where you are in your MCMC or optimization. And you would, for the case of a central, say you have NSEN equals a half or a third in a halo of a given mass. Draw a uniform random number, and if your uniform random number is below a third, then you put a central there, and if it's above, then you leave it empty. And so this is the way in which you have then centrals that populate your universe. Similarly, for satellites, you would draw from a Poisson distribution centered at the average number of satellites that fit in that halo. That would tell you how many satellites belong in that halo, and then you would sprinkle them in according to an NFW profile. So think about what you have at the end of that exercise. You have a catalog of host halos, and now you have essentially a set of points that have no features at all other than the fact that they represent galaxies that are in your sample. They don't have masses, they don't have colors, they don't have anything. So even for fits to color-dependent clustering, all that you know at the end of the day, after having populated a universe that has good clustering that matches what's seen in SDSS, is the muck galaxies in your sample are in this reddest bin. You don't know what color they actually are, then you just know that it's in the particular range that's the same range that you're fitting to. The CLF operates in a different way. In the CLF, the conditional luminosity function, the galaxies do have attributes. They have one attribute, they have a luminosity. So the idea of the CLF is, as a function of halo mass, I'm going to specify the luminosity function of centrals that live in that halo mass. And for satellites, I'm going to specify the luminosity function of satellites that live in that halo mass. These two techniques for halo occupation modeling, they are very intimately connected. So the one is the integral of the other. If you integrate the CLF above some luminosity threshold, then you have just derived the HOD that's directly implied by that CLF. It's a little bit more fiddly to derive a CLF from an HOD because you need to take finite difference derivatives in order to take the derivative of two different threshold samples to get the HOD, but you can do it. So the one is the derivative of the other. So again, with With the CLF, oh yeah, right. So historically, the CLF was developed basically at the same time as the HOD, but independently by different authors. So we saw different ways in which the functional forms of the HOD were motivated by hydrosims, by semi-analytic models, by subhalos. So the CLF folks took a different approach to motivate their functional forms. They use galaxy group catalogs from SDSS. They went to a catalog of SDSS galaxies, they used a galaxy group finding algorithm developed by Xiaohui Yang and company to group together centrals and satellites in the sky, centrals and satellites in the sky. And then they observed, okay, the central galaxy in this group and in this group and in this group, all as a function of common halo mass, looks like it has a log normal luminosity function. And so they used this observation to motivate the functional forms for the CLF for centrals, which was just a log normal luminosity function. And likewise for satellites, they observed, if I just plot a histogram of the luminosity function of satellites in a given halo, then I have a Schechter-like luminosity function. I have a power law, maybe with a rolling index that then scales and falls off exponentially as you approach the luminosity of the central. So these are just a different way in order to motivate the functional form that they use for the CLF that then they use to, a programmatic sort of MCMC to then optimize to galaxy clustering and lensing in order to determine what the best fitting parameters are to given samples. So this is what they did. So some results that they derived, sort of using these CLF techniques in the mid-2000s, were in this case, this example shown here is the scaling relation between essentially the mass to light ratios. So for central galaxies, the halo mass is on the horizontal, and the vertical axis is the central galaxy luminosity. And the posteriors on this scaling relation are shown here in Frank's purple shaded bands with points with error bars come from SDSS measurements from the galaxy group catalog. And then another inference that we make using these techniques is how the satellite fraction scales with luminosity. So again, the shaded bands show the posterior confidence intervals on how FSAT, as a function of luminosity, what fraction of those galaxies are satellites. And the basic scaling here makes sense. So at very high luminosity, you're unlikely to be a satellite. The brightest galaxies in the universe are all centrals. And as you go towards fainter galaxy samples, you're much more likely to be a satellite. Okay, so how do we do cosmological inference with these techniques? You basically have two classes of approaches. Either you take sort of an analytic fitting function type approach based on the halo model, in which you have fitting functions that you derive for how what's shown here. So the halo mass function and the halo bias function scale with halo mass and redshift. You have some analytic fitting functions that describe these scaling relations. And then you can write down how, well, so then analytic fitting functions for these relations tell you, okay, so I know the abundance of dark matter halos as a function of their mass. I know how dark matter halos as a function of their mass, how their clustering behaves. And so then if I know how to sprinkle galaxies into host halos, well, then I know the abundance of galaxies as a function of their luminosity. In this case, that comes directly from the CLF. And then if I know how dark matter halos cluster together, and if I know their radial profiles, well, then I know how galaxies should cluster together. On large scales, it's just a weighted, if you know the clustering of dark matter halos on large scales, then you just take a weighted combination of that clustering in order to get the clustering of galaxies on large scales. And then if you know how the internal structure of dark matter halos, if you know the radial profile of the halos and you know how galaxies trace that radial profile, then on small scales, you can compute the two-point clustering. And then you can make a prediction across the full range of scales via analytic fitting function methods to derive predictions for galaxy clustering. Then run your MCMC as a function of cosmology. Cosmology changes the abundance of halos, it changes the clustering of halos, and you can compute that programmatically using the halo model and derive cosmological constraints on omega matter sigma 8. This is a paper from 2013 in a series of papers using the CLF in the early 2010s for this exact purpose, using SDSS galaxy clustering and galaxy lensing to derive posteriors in omega matter sigma 8, here shown with the blue contours, compared to best fitting contours from WMAP, from the CMD. An important feature of these constraints is not just that they're reasonably tight, but also that they are quite complementary to the constraints that you get from the CMD. So the degeneracy directions are completely different. So you're getting a qualitatively different handle on cosmology by going after large scale structure in the nonlinear regime, in this case using the CLF. Okay, so that approach was really one of the earliest examples of deriving full stop MCMC Bayesian posteriors on cosmological parameters using galaxy halo connection. So analytic fitting functions, these methods do have their limitations. It's very difficult to do a much more accurate job than was achieved in this paper because of underlying limitations of fitting functions that you assume are able to describe the abundance of dark matter halos as a function of their mass across redshift. So this is an example of a fitting function that was used for this purpose. This is a paper by Jeremy Tinker, developing from a suite of cosmological simulations, measuring the dark matter halo mass function over and over again in cosmological boxes of different cosmology, measuring the halo mass function, building a fitting function that describes the abundance of halos as a function of mass and as a function of cosmology. This is one of the most widely used fitting functions for this purpose. As far as analytic approximations are concerned, this is the case. And one of the basic takeaways, even though this is a very widely used fitting function for this purpose, one of the basic takeaways of this paper is that fitting function-based descriptions of the halo mass function are really only accurate to the 10 to 20% level. It's just very challenging to capture the complexity of the abundance of dark matter halos just using an analytic fit. So are we stuck? So how can we go beyond this? So if we really want to get much tighter contours on cosmology, how can we overcome this limitation of the challenge of describing what's in simulations with a fitting function? So machine learning is the answer that has emerged in the field to address this problem. So this is an alternative to a fitting function approach. So in this approach to the problem, to doing cosmological inverse of the galaxy halo connection, you make no attempt to write down an analytical description of halo bias or halo mass function at all. Instead, what you do is you start with a suite of cosmological simulations, and in each simulation, you pick your choice of HOD parameters, sprinkle galaxies in, measure the 2-point clustering of the galaxies, and rinse and repeat this exercise in each box many times for different HOD parameters in this box and then in this box, and then build an emulator that says, if you give me cosmology and the HOD parameters, I will in return give you the 2-point clustering. So this is a classic problem for emulation, for an ML emulator, since it's essentially just interpolating between a set of on a finite grid of previously tabulated results. And so this is a paper led by Zhangju Zhai a couple of years ago using the Amulus cosmological suite of simulations for this purpose. Let me briefly point out, so especially in 2025, people hear AI, ML, or even machine learning, they assume that it was a neural network. It's very expensive to run suites of cosmological simulations spanning a wide range in cosmological parameters. Training a neural network requires enormous quantities of training data. You have hundreds of thousands or millions or more of parameters, so you need tons of training data. And so it's quite impractical to train a neural network to capture the cosmology dependence of galaxy clustering using directly simulated cosmological boxes. If you use a neural network, if you use a Gaussian process algorithm, this is a classical ML technique. This is not an AI technique. Essentially, it's a non-parametric interpolator, which has this nice property of having very well controlled and characterized errors on the interpolation. It's a very well suited technique for this purpose when you have limited training data. And instead of an analytic fitting function, but using an emulator, Zhangju Zhai and co. derived constraints on cosmology. With the same kind of technique, fitting 2-point clustering, in this case, I believe this was redshift-based clustering, to derive constraints on omega matter, or in this case on sigma 8, and actually gamma f in this paper was a nice trick that they used to sort of mock up a particular deviation, particular form of modified gravity. So this is an example of sort of two things. One, using machine learning to be able to make predictions for the galaxy halo connection in the nonlinear regime, and also revealing not just good cosmological constraints in the nonlinear regime, but also the ability to constrain modified gravity. Okay, so what are some additional challenges? So one challenge that we sort of saw was that fitting functions are difficult to sort of capture the clustering and abundance of dark matter halos, and that machine learning offers a solution to this problem. Another major limitation of halo occupation modeling in general. So notice that throughout this lecture, I've only described how galaxies occupy halos as a function of their mass. But halo mass alone does not determine the clustering properties of the galaxy, does not determine the clustering property of the halo. In general, the clustering properties of halos depends on more than halo mass, and that additional dependence falls under the sort of general catch-all term, halo assembly bias. So what you're looking at in this figure is the large-scale bias of dark matter halos of on the horizontal axis of a fixed mass. Previously, you've seen halo bias functions that depended only on mass. So you've seen these calibrated fitting functions. So as a function of mass, you can read off what the bias is. And remember bias is the strength of two-point clustering above and beyond the clustering of the dark matter, above the matter density field. So you can compute it in a straightforward way. So you just go ahead and you count pairs of halos as a function of their radius. On very large scales, if you compare those pair counts to the pair counts of the dark matter particles in your simulation, that ratio and its square root is the halo bias. If you repeat that exercise not just for halos of a given mass, but also for halos of a given formation time, then the clustering strength of the halos is a very sensitive function of the halo assembly. And generally speaking, say for Milky Way mass halos, older halos cluster substantially more strongly than younger halos. So this is potentially a major limitation of halo occupation models, because now all of a sudden, if your galaxy halo connection, if the way in which you sprinkle in galaxies should depend on halo age and not just on halo mass, well then by assuming that halo mass alone determines the galaxy content of a halo, you can make a potentially grossly incorrect prediction for the two-point clustering, like factor of 2 or 3 off. So let's see. So okay, so this result, which is this is a plot adapted from the paper that sort of introduced the world to this concept of halo assembly bias from Gao and White based on the Millennium simulations. It's not just true for halo age, for the formation time of halos, but it's true for like just about any halo property you can think of. So this is a nice paper from several years ago by Andrés Salcedo, in which he took halos of a given mass and he split them by formation time, he split them by concentration, he split them by halo spin, and then looked at how the clustering properties on large scales depend on these secondary halo properties. And so what you're looking at in this figure is on the y-axis is just the ratio of the clustering strength. And you can see not only does halo clustering depend on halo properties beyond mass for all these different halos, but also the strength of that dependence is itself mass dependent. And that mass dependence is itself dependent upon the choice of the secondary property, which is just by way of saying it's a big, complicated world out there for the way simulated halos cluster. And so this naive assumption that halo mass alone tells you the clustering is a very poor description for the true clustering properties of dark matter halos that we can directly simulate and predict. So we can sort of run a simulation and get a sort of numerical approximation that's as accurate as you want, provided you have a big enough box to predict how the halos should cluster as a function of all these secondary properties. But the assumption that halo mass alone describes that turns out to be very poor. So we can run our simulations, but the use of these fitting functions, no matter how accurate they are, is not going to capture this effect at all. And so for me, this result, together with the sort of series of observations Andrés was, many authors have found this sort of same thing, this complex multidimensional dependence of halo clustering. To me, this is just a major motivation for simulation-based modeling. Because if you're stuck before you can even make a prediction for galaxy clustering, if you're stuck first having to calibrate analytic scaling relations that depend on all of these properties before you can even write down a prediction, it'll just be very challenging for you to be able to ever, in a reasonable amount of human execution time, complete an analysis. Whereas if you can just write down a galaxy halo connection model that includes these dependencies, and then just use simulation-based methods to compute the two-point clustering, well, then you can capture the effect as accurately as you're able to simulate it in the underlying halos. So a natural question that comes up, well, let's see. I think I have enough time to do this. Okay, so you might wonder, well, okay. I've been talking about halo clustering as a function of, we're talking about halo assembly bias as a function of halo bias. So on very large scales, you have these dependencies for the clustering strength that depend on multiple properties. But it's not just on very large scales where clustering strength varies, but it's the full spatial distribution of halos that depends on multiple halo properties at once. So what you're looking at in this figure is not just large scale halo bias, but the scale dependence of halo assembly bias. So if you compute the 2-point correlation function as a function of scale of old halos versus young halos, or high Vmax halos versus low Vmax halos at the same mass, then there's this pronounced scale dependence that you see that sort of peaks around 1 to 2 megaparsecs in this 1 to 2 halo transition regime. And that scale dependence itself depends on mass. So this y-axis, when this y-axis is positive, it just means that high Vmax halos cluster more strongly than low Vmax halos at the scale in question. And so for me, it's really this scale-dependent result that makes it seem kind of hopeless to be able to have an analytic fitting function that can describe all of these different secondary halo properties dependence, including the scale dependence, which has this complex behavior. A really nice paper led by Sierra Villarreal, in which what she did was she studied whether or not it's possible to just redefine dark matter halo boundary such that if I make an appropriately judicious choice for what the halo boundary is that divides subhalos from hosts, maybe I can explain away halo assembly bias. So that's partly motivated by this result. You can see that if I include all halos of a given mass in the top panel versus I exclude anything that was an ejected halo, which is to say it's a halo that temporarily at some point in its past history passed inside the VOE radius of another halo and then continued on about its way. If you exclude those halos from the computation, then you get a significant reduction in the signal. So that's partly motivation for considering, well, what if I just used a more relaxed definition of dark matter halo, such that that thing that passed through and then went away and became essential is actually, we should be calling that thing a subhalo anyway. So maybe I should just use a more relaxed definition of the halo to define my boundary. Unfortunately, that doesn't work. It does ameliorate the problem for a particular range of scales and a particular range of halo mass. But what she found in a pretty exhaustive study of this effect was that no matter what definition you use, on some range of halo masses and on some range of scales, you still have very significant effects of halo assembly bias that are going to impact your predictions. And so it seems to be something that we just need to live with in the galaxy halo connection. So how do we live with it? Well, we can build models that capture it. So this is an example of a model of the halo occupation distribution in which the number of galaxies that I sprinkle in a halo depends on more than just halo mass, but for example, on halo age. So all the halos of a given mass in this decorated HOD approach, I called it, you have older halos that, so I'm gonna, for halos of a given mass, I'm gonna have some scatter about whether the number of galaxies that I sprinkle in is, on average, maybe it's 2, but some halos get 1, some halos get 3. I'm going to have that scatter correlated with the secondary halo property, such that older halos will tend to get larger draws of the number of galaxies, and younger halos will tend to get fewer numbers of draws of the number of galaxies. And so I have a secondary dependence on the abundance of halos as a function of the secondary property. And then if you just use simulation-based methods, well, then you can just directly compute what the 2-point clustering is in a way that, that captures all of this nonlinear scaling relations. Because I'm just directly having the simulated halos determine the prediction for the clustering. Oh yeah, I should just point out, so this is one method of doing this, but so there's actually now, this is now, I think, become more of an industry standard technique for being able to build models of the galaxy halo connection. If you really want to describe DESI precision data with an HOD, then you just need to capture effects beyond standard halo mass predictions. And so there's actually many different ways in which this is implemented. I've linked to a couple of them here. This is an analysis led by Johannes Lange in which he analyzed BOSS clustering using this decorated HOD, using an HOD that has this secondary dependence on concentration in this paper. And he did this exercise where he repeatedly populated different boxes with an HOD, computed the clustering, and then derived cosmological inference by leveraging this cosmological suite of boxes. Brief sidebar, Johannes has this very clever method for doing cosmological inference with a box of with a suite of boxes that doesn't actually ever build an emulator. Instead, at each box, you just run your MCMC to completion using nested sampling so that you can get the Bayesian evidence. And then in this box, you run your MCMC to completion. And in this box, and this box, and this box. And then you have the evidence, if you use nested sampling, as a function of cosmological parameters. So this is the evidence at fixed cosmology. So this is essentially the evidence after having marginalized over the galaxy-Hale connection. What's the likelihood, or what's the Bayesian evidence of that particular cosmological model? But that just is the cosmological posteriors after marginalizing over galaxy-Hale connection. And so that's the sort of different, I think, technique that Johannes used to capture the cosmology dependence in this analysis. It's just an alternative to using direct emulation. Let's see. Let me make just a brief note. So halo assembly bias is still, I think, a major challenge of halo occupation modeling. That's still a preoccupation in many different DESI analyses, for example. So are just the functional forms that we need to use to describe the halo occupation distribution. So I said earlier when I motivated the form of the HOD that at sufficiently high mass, you should asymptote to having one galaxy in your sample. But if your galaxy sample is selected through some complex means, then there's no guarantees that you need to have one galaxy. That, for example, an emission line galaxy at high mass, you should expect to have very few, if any, emission line galaxies sitting at the dead center of a cluster mass halo. And so instead, you have different functional forms that you need to both motivate and then run on your observational data analysis. And so this is another area of active research for realistically complex galaxy samples that are in our observations. What should the form of the HOD be? Another major challenge of HOD cosmology today is just the computational demands of simulation-based modeling. So okay, you can get these improved accurate predictions beyond what can be achieved with fitting functions, but you need to run a dang cosmological suite of high-resolution boxes with large cosmological volumes, and it's a huge demand on just the raw compute of producing these simulations. And even once you've produced such a suite, well, what if you find that the particular cosmological parameters that you chose, they didn't have for example, they didn't have neutrino mass, or maybe you only simulated lambda CDM, but now all of a sudden we're finding W0 WA is an interesting parameterization. Well then, dang, now you need to run a new suite or find some clever way to augment what you already ran with additional boxes. So okay, that was kind of a lightning tour of some potential gains of halo occupation modeling, some advantages and also some challenges. This is my last slide. I mostly just want to recap what I've shared with you all of these last few lectures. So the nonlinear regime of cosmology, I think, is an exciting frontier of contemporary research, and it's just very powerful. Has tons of constraining power that you can reap that just give a kind of qualitatively new handle on cosmology that's just not possible when you restrict attention to the linear regime. But now all of a sudden, you have many, many more systematics that you need to worry about, sort of root level theoretical systematics in your uncertainty quantification. So it's very challenging, requires lots of modeling effort in order to be able to derive robust and reliable constraints, despite the fact that it's very powerful. And I also think there's some really nice intersections with sort of state-of-the-art AI ML. So emulation methods, I think, are a very exciting area that I think will just continue to see more and more standard in the field. And then an area that's particularly exciting to me is differentiable programming. And the complexity that all of a sudden you can capture in the galaxy-Hale connection by having a differential model is just leaps and bounds beyond what can be achieved with a small number of parameters with a non-differentiable model. So yeah, then my main takeaway really is just that this is a field with lots of exciting challenges and that new ideas are needed from young researchers like y'all. So thanks for your attention.
Great, thank you, Andrew. Maybe we have time for 1-2 questions before some closing remarks.
Sorry, this is really specific. Can you go back to the previous slide? Okay, the previous one then. Sorry. Yeah, so you have written there that the LRGs have a completeness fraction cutoff. My understanding is that that happens in redshift 0.9, but I actually don't understand why. And if you can just say like something about
Sure. So if your galaxy sample has not just a luminosity cut, but it also has a color cut, well then all bets are off that you must have a galaxy at sufficiently high halo mass that should have that set of colors. So if you forget the color cut and you go towards arbitrarily high halo mass, 10 to the 16 solar masses, well then for sure there's some galaxy that sits in its center. But there's no guarantee that a red galaxy has to sit at the center, unless you assume that 100.0% of massive galaxies are red according to a given color cut, then you don't asymptote to unity. You asymptote to some value below unity. And who knows what that is? It depends on the color cut. It depends on the galaxy sample, and that may depend on redshift because the abundance of galaxies as a function of color changes with redshift, right? So, yeah. So that's maybe is that a at least high level picture of why that happens? Okay, great. Yeah. I'll repeat the question. Yeah, I think.
Oh, just throw it on. Sorry. So I'm a bit confused on like I guess the difference between like a halo occupation distribution and like a sub-halo mass function, because it's like to me, it seems like they're kind of like telling you the same thing, like the number of, so one tells you like the number of galaxies in like a halo, and the other one tells you like the number of like sub-halos in a halo.
Right.
And I know that sometimes like they assume that like a sub-halo has a galaxy. So
Right.
I'm not sure, like, are they probing different things or?
So yes and no. One of the basic takeaways for me from subhalo abundance matching is that galaxies live in subhalos. But which galaxies? So if I make a particular kind of cut on my observed galaxies, well, there's no guarantees that this subhalo here has to host a galaxy of that type. And the HOD says, what is the number of galaxies of that type that live in that halo? Whereas the subhalo mass function just says, what is the abundance of subhalos that live in that halo? And you see what I mean?
Yeah, that makes more sense.
Great, yes. The HOD is more flexible because its parameters can adjust to capture the fact that you've made some non-trivial cut.
Right. Okay, that makes sense. Thank you.
Great, yeah.
Right, hello. Could you explain a bit more about how the cosmological evidence modeling works? And is this something that, similarly to the Gaussian process, would give you will you overcome the requirement of neural networks of having a large training sample?
Great, yeah, sure. So let me sketch just the basic idea one more time. And the best way to understand this in detail is to follow the link to the Johannes's paper, to his first paper on this topic. I think he goes over it in full mathematical detail. So one more time, just let me sketch the difference between emulation and cosmological evidence modeling. So if you're going to use simulation-based modeling to do cosmological inference, in some way or another, you gotta have different galaxy populations as a function of different cosmological boxes. You're going to have to create a bunch of galaxy populations in each one. In emulation, what you do is you repeatedly compute the same data vector, like the same galaxy clustering in bins of R. And you create a training sample as a function of both cosmology parameters and HOD parameters of that data vector. And then you just use an emulator, an interpolator, to give you the predicted data vector. And then you run your MCMC using the emulated data vector instead of the real one. Okay. In evidence modeling, you do something qualitatively different. You, at fixed cosmology, you use the exact two-point correlation function computed from the simulation-based method in order to predict your data vector. And you march through your MCMC all the way to completion. An important detail here is that you use nested sampling so that you have the Bayesian evidence at the end of the day. So now I march through my, my nested sampling, and I have the evidence of this particular cosmology. And I do that in this box, and then I do that in this box. So a nice feature of going about the computation in this way is that now I can have a much more complex galaxy model, and I don't have to worry about whether my emulator got it right, which can actually be very challenging. We're always operating at the hairy edge of, do we have enough simulations? Because they're so expensive. That's always the regime that we're in. And so if you never use an approximation for your data vector, then you can just capture a more complex model such that you're not limited by the accuracy of your emulator. The evidence, so at the end of the day, what you get is an evidence as a function of cosmology. So that's the evidence essentially having marginalized over the uncertainty in the galaxy halo connection at fixed cosmology. But if you have the evidence now as a function of cosmology, that is directly related to the posteriors on the cosmological parameters. Low evidence models will be unlikely cosmological parameters, and high evidence models will be the most likely cosmological parameters. So the mathematical detail for how exactly you derive posteriors, I would refer you to Johannes' paper, but that's the sort of key idea. And I think it also sketches sort of why there's this advantage of it. It allows you a more natural way to capture sort of realistically complex galaxy halo connection models without having to worry about, did my emulator capture what I needed? You see what I mean?
Thank you then.
If there are no more questions, Andrew, thank you again. Thank you, thank you. And I will just use the opportunity to say a few more words. First of all, on the behalf of local organizers, to thank our wonderful lecturers for informative, detailed, very carefully prepared talks, Andrew and Will and all of the others who are not here, who have departed already. And to you participants for coming from